Hello, I'm Vivian Lai from the University of Colorado Boulder, and I'll talk about how model-driven tutorials can help humans understand embedded patterns in machine learning models. This is joint work with Han Liu and Chenhao Tan. Thanks to its superior predictive abilities, machine learning has increasingly made its way into our lives, especially in societally critical tasks such as medical diagnosis, recidivism prediction, hiring processes, and autonomous driving. In order to unlock the full potential of AI and truly benefit our society in critical tasks, we need AI to effectively collaborate with humans and enhance human performance. And the important ingredient of this process is explanations. While the research community has proposed a variety of ways to derive explanations from machine learning classifiers, the explanations might not be fully understandable and at times confusing to humans. Here, we're looking at the case of deceptive review detection, where the goal is to distinguish deceptive reviews from genuine reviews. The highlighted words here represent explanations or important features from the machine learning classifier. Green words are associated to genuine reviews, and red words are associated to deceptive reviews. The darker the color, the more associated the feature is to the label. These highlighted words also tell us why the classifier predicts the review as deceptive. Without any context or assistance, it is non-trivial for humans to understand why certain words are associated to certain label, much less identify any patterns from the model. For instance, the word Chicago is a big clue to why the review is predicted as deceptive. Because apparently, Chicago is highly associated with deceptive reviews as people are more likely to mention the city name instead of specific places when they imagine their experience. As such, this very example shows that explaining AI can be very tricky, and hence our title, Why is Chicago Deceptive? To understand why explaining AI is tricky, we first need to recognize that there are two distinct types of AI learning modes. The first one, emulating human intelligence, and the second, discovering new knowledge. In tasks such as object recognition, the AI emulates humans' abilities as humans can easily perform these tasks. When a human is asked to identify the two objects in the slides, the human will be able to recognize that the two objects are a dog and cat respectively. However, on the other hand, tasks such as detecting deceptive reviews are challenging for humans, but the AI can discover new insights from the model for humans. Looking at the same example from previous slide, we know that the AI can identify the following pattern. Deceptive reviews are often less specific. To summarize, AI can discover inconspicuous and counterintuitive patterns to humans in the discovering mode. To make explaining AI less tricky, we propose model-driven tutorials in the training phase that elucidate counterintuitive patterns and enhance humans' ability to understand these patterns. We consider two types of model-driven tutorials. First, we use guidelines from scientific papers. These guidelines are state-of-the-art science communication. For instance, journalists typically summarize academic papers into such lists. Second, we consider example tutorials that are automatically selected by different algorithms. SP-LINE and our novel-spaced repetition algorithm. SP-LINE is an algorithm that selects examples to provide great coverage in the training set so humans can have a more holistic understanding of the data set. Our spaced repetition algorithm leverages insights from the education literature regarding the effectiveness of spaced repetition. It is created such that users can be exposed to important features repeatedly with gaps in between. And ideally, when exposed to important features repeatedly, humans can better retain important information in the long run. In our interest of time, we focus on spaced repetition in this talk, but please refer to our paper for more details. We will now look at the experimental design and research questions. Our experiment has two phases. We first get participants to go through a training phase, then they enter a prediction phase, which will be used to measure human performance after model-driven tutorials. We study three research questions in our paper. The first research question investigates the effect of different tutorials in the training phase, where participants are exposed to different tutorials, and no assistance in the prediction phase, where they are tested if the tutorials help improve their performance. In short, research question 1 investigates the effect of different tutorials during the training phase. Like what we saw before, we can also show highlights on words in the prediction phase as some form of real-time assistance. This may improve the effectiveness of the training phase by reminding people of those patterns. The second research question then investigates the effect of real-time assistance in the prediction phase. All participants see the same type of tutorial in this experiment, and we use the spaced repetition algorithm to automatically select the examples. Instead of no assistance from the machine during the prediction phase, participants are exposed to different types of real-time assistance, and we compare how each type of real-time assistance affects the human performance. In short, research question 2 investigates the effect of real-time assistance during the prediction phase. The past two experiments use explanations from a linear classifier. Deep learning models have been gaining popularity due to their superior predictive abilities. Therefore, we wanted to find out how well our results would generalize. In other words, research question 3 investigates the effect of model complexity. Before quantitative studies are conducted, we also perform qualitative study to gather feedback on the web interface design and general process. Please check out our paper for that part. Now, let's dive into the results of research question 1. In research question 1, we want to find out if human performance will improve in the prediction phase when exposed to different types of tutorials in the training phase. Our results suggest that model-driven tutorials are useful in improving human performance to some extent. The difference between the control and guideline setup is statistically significant, and the difference between control and spaced repetition guidelines is borderline significant. However, we do not find statistically significant difference between spaced repetition and SP-line, which is why we focus on spaced repetition in the experiment. We think that the tutorials have limited usefulness as it is challenging for humans to remember the patterns from the training phase. Quoting verbatim from a participant, "The tutorial is helpful, but it's just hard not being able to reference it." Due to the limited effectiveness of tutorials, we recognize that humans should be provided some assistance during the prediction phase. In the second research question, we want to find out if exposing participants to various levels of real-time assistance in the prediction phase would affect their performance. Here, the spectrum shows the different levels of real-time assistance between full human agency and full automation. Overall, the amount of information from the machine learning classifier increases along the spectrum. To further illustrate the spectrum, we highlight the differences between unsigned explanations and signed explanations. Unsigned explanations do not reveal the class of the feature. In this context, the feature Chicago is the most important feature, but it does not tell us if it's a deceptive or genuine feature. On the other hand, Signed explanations reveal the class of the feature. The feature Chicago is highly deceptive, while the feature very is highly genuine. Results from experiment 2 suggest that real-time assistance can indeed significantly improve human performance to above 70%. The differences in the setups shown compared to no assistance are statistically significant. However, the difference between signed explanations and signed explanations with predicted label, guidelines, and accuracy is not statistically significant. This suggests that signed highlights are effective and sufficient. In other words, human performance does not gain much from presenting additional information from machine learning classifiers. Overall, while performance has shown significant improvement, there still exists a gap between best human AI performance and AI performance. This is consistent with a lot of recent results. If you're interested in bridging this gap, please check out our workshop paper and our discussions in that paper. And the link to the paper is provided in the last slide. In our final research question, we want to find out if results from experiment 1 and 2 can be generalized in other models, since explanations in experiment 1 and 2 are derived from a simple model. In this experiment, we compare human performance when exposed to explanations from different types of models, specifically BERT. This slide shows an example of how SVM and BERT attention explanations differ. In SVM, we extract top 10 coefficients in a linear model. And in BERT attention, we retrieve attention values from its built-in attention mechanism. Do note that explanations from BERT attention are unsigned, as attention values from BERT are between 0 and 1. This slide shows an example of how SVM and BERT-LIME explanations differ. In BERT-LIME, feature importance comes from LIME by fitting a sparse linear model to approximate local model predictions. And similarly, we retrieve top 10 coefficients from both models' explanations. We find that methods of deriving explanations make a significant difference. Human performance is consistently better when important words are derived from simple model as compared to deep models. As such, it is fair to claim that simple models are preferred when serving as explanations to support human decision-making. We think that one reason is that explanations from linear models are more consistent and show less diversity. Further, we hypothesize one of the reasons why BERT attention performs poorly is due to the fact that it doesn't give very meaningful representations. For instance, periods are highlighted as the most important feature, and it is difficult for humans to understand why periods are important in this context. Additionally, we find that training leads to better human performance as compared to no training. Humans achieve better performance with training with any kind of explanation methods. Differences among all pairs of treatments are also statistically significant. We have now come to the end of the presentation, and here are 3 main takeaways. Firstly, model-driven tutorials are helpful to a certain extent in improving human performance. Secondly, while deep learning models have superior predictive powers, explanations from simple models are more preferred by humans as they are more interpretable. And lastly, despite introducing tutorials and explanations, human performance is still relatively limited, as there still exists a gap between human AI performance and AI performance. Limited improvement in human performance suggests future directions for human-centered tutorials and explanations. We also discussed this in our workshop paper on how we can harness explanations to bridge the gap between human and AI. The links to our full paper and workshop paper are on the slides, and our public demo is available at machineintheloop.com. Thank you so much for listening.